First of all, it's a great pleasure to be here, and especially to be speaking at the same time as Jean-Pierre Ramis, whose papers inspired lots of my work. So the initial impetus came from this remark of Dubrovin. He had this large paper in like 1993, which was published in Lecture Notes in Math 1620, and in there he pointed out that there's this space of Stokes data, which from his perspective was supposed to be a moduli space of two-dimensional topological quantum field theories, and basically it was got by starting with the work of Chikotty and Vafa, who were counting BPS states. So they would have some Stokes matrix with integer entries which counted the number of solitons which go between vacua, and it's as if Dubrovin complexified the story and replaced the integers by complex numbers, and found that there's a natural braid group invariant Poisson structure on here, which in the simplest case explicitly is written like this, with the action of the three-string braid group there, and this preserves this cubic function, the Casimir, which is basically the trace of S transpose S inverse. And in particular, you can look at the quantum cohomology of CP2, which corresponds to the particular point x equals y equals z equals 3. And the fact that that has an infinite braid orbit was proved by Markov in 1876, and people often speak of this as the Markov cubic. The generalization of this formula to the m by n picture was in a paper of Ugalia, a student of Dubrovin, in 1999. So I wanted to understand more intrinsically where this type of braid group action appears. Now, in this particular example, it's easy to do a Laplace transformation and relate it to a tame isomonodromy problem, basically braiding of points on a Riemann sphere. But it's pointing out that there is this phenomenon of braiding of Stokes data, and the question became to understand what is the general picture, what are the braid group actions and the Poisson structures which occur in moduli spaces of Stokes data, which we now call wild character varieties. So the basic picture we want to get to will, roughly speaking, be something like this. We'll have two vibrations over the same base. So there's this base B, and there's a vibration over here. So the basic point is that this embeds in the isomonodromy the higher order versions of panel of A systems, and all of these are modular. They can be obtained by thinking about moduli spaces of connections on curves. So we'll spend most of the time speaking about moduli spaces of algebraic connections on open Riemann surfaces, or open smooth algebraic curves. But the motivation comes completely out of trying to understand these non-linear questions. So basically there's a vibration here, and the fibers of this will be the Dirac moduli spaces. So basically moduli spaces of connections on curves, and eventually having particular poles. And then there's a kind of a Riemann-Hilbert-Birkhoff isomorphism, which is a complex analytic isomorphism to some space of topological data over here. This is the Betty picture, and I'm also including the Stokes picture in that as well. And the basic geometric thing that the isomonodromy equations are is a flat, complete Ehresmann connection on this bundle of Dirac moduli spaces over here. And this is analytically isomorphic to a local system of varieties, the local system of wild character varieties, when you deform the parameters. And so most of the talk today will be spent trying to make a precise definition of what we mean by the parameters of the base. So basically we need to fix a curve with some marked points and an irregular class, and we'll talk about what the irregular class is. And so basically, perhaps I'll fix this now. And so sigma is a smooth, compact, complex algebraic curve. Compact algebraic curve. And we want to fix it some points, and so A is a bit A1 up to AM is a finite collection of points. Okay, so having fixed that, we then want to look at the moduli spaces which occur. I want to talk about an approximation. In order to get this precise picture, we need to do something technical. So I want to speak about a simplified picture to start off with. So let me erase this and draw a big picture on the board of how this works. And so that's the basic aim. But now I want to draw a big picture to just point out sort of how the moduli spaces occur and sort of what the basic parallel picture is between the better known tame picture and where we want to go. So we want to look at the category of connections on the punctured curve. And so sigma O is sigma minus these marked points. And so we'll, so here I want to look at the category connections. So this consists of pairs consisting of a complex algebraic vector bundle on sigma O. So a connection is a pair E nabla, where E is an algebraic vector bundle, say of rank n, on this open curve. And so here it's enough to take as a risky locally trivial, so I can have these open patches and clutching maps to define that. And nabla is an algebraic connection on this. And so it's a map from the sheaf of sections of E to the sections of E tensored with algebraic 1 forms omega 1. And this has to obey the Leibniz rule that if I act by nabla on a locally defined function and a section S, then this is equal to df S plus f nabla of S. So for example, we could take the curve to be the sphere, so sigma to be P1, which contains the complex plane, and take E to be trivial. And I could just take nabla to be something like D minus A, where A is a matrix of meromorphic 1 forms. And so A is a some, okay, it has some poles, and so it's a matrix, an n by n matrix of meromorphic 1 forms. So e.g., I could look at the sum of like ai over z minus small ai dz, a particular example of a Fuchsian system. For constant matrices ai here. So we want to look at the category of connections on this open curve, and the basic fact is that this category has a purely topological description, and I want to spend this lecture and perhaps the one tomorrow describing it. So we want to attach certain pieces of purely topological data to an algebraic connection. So the simplest thing to do is to look at the local system of solutions. So this is a functor to the category log_sys, so of local systems of finite dimensional complex vector spaces. So here I'm working purely topologically and just having a look at small open disks. So suppose I have an open set, so U in sigma O. I want to define what is the section of the corresponding local system there. So I'll do V of U to just be the analytic solutions of the corresponding connections, which is just the sections of nabla analytified, or the kernel of nabla applied to E an. So Cauchy tells us that we get an n-dimensional vector space if I have a small complex disk U, and so this thing V gives me a gadget which attacks a finite dimensional complex vector space to each small open set, and these gadgets can be axiomatized to give the definition of a local system. So So a locally constant sheaf of finite dimensional complex vector spaces. Here it will be of dimension n, where n is the rank of the vector bundles that we fixed at the start. Okay, so this is a very abstract thing to do, and one can make it more explicit. First of all, let me just point out that there's a subcategory, the tame connection, so con RS, the regular singular or tame connection, such that if I restrict to look at the local system of solutions of these, I have an equivalence between this purely algebraic category here and this purely topological category of local systems. And so RS just means regular singular, which for me means the same as tame. So there's various different ways to define it. You can say that your bundle has an extension across the puncture such that the connection has most first order pole, or it's equivalent to looking in an algebraic trivialization at the puncture, looking at the rate of growth of solutions as you go towards the pole, and you want to have at most polynomial growth, no exponential terms. So that defines a subcategory, and this functor of taking the local system of solutions is an equivalence. So we have this purely intrinsic description topologically of the category of regular, singular, or tame connections. So this is slightly pedantic because we can describe this very easily in terms of the space of representations of the fundamental group. People did lots of work in 1890 and things to define what is the fundamental group. So let me restrict to the local systems of rank n, log sys n, if you like, the subgroupoid, so just taking the morphisms to be isomorphisms, the ones of rank n, and then we can look at the set of isomorphism classes here. And then we can choose a base point. So let me go on to the next board. So we can get to HOM, so pi 1 of the punctured curve with respect to some base point b. So here we made no choices at all. Here we're now fixing a base point as well. I'll define G to be this group GLNC. And we're looking at the space of representations of this fundamental group into G. And we want to look at the set of orbits, first of all. So the fact is that on the top here, we have this affine complex variety. And the set of isomorphism classes is exactly the set of orbits of G acting by conjugation on this set of representation of the fundamental group. So this category has the nice property of being the set of orbits of a complex reductive group on an affine variety. So then what we want to do is replace this set theoretic quotient by the affine GIT quotient. Just take the variety associated to the ring of G invariant functions. So if we do this GIT, then we get a variety, and we'll call this the character variety or Betty moduli space. So this is the character variety. So it's an affine complex algebraic variety of a Betty moduli space. So yeah, this is an algebraic Poisson variety. And the symplectic leaves are of the form MBC contained in MB. So you want to fix the conjugacy class of monodromy around the punctures. And so C is like C1 up to Cm, where Ci contained in G is a conjugacy class. So if you take the orbits to be simple, you get something which is still affine, otherwise it's quasi-affine. It's an open part of an affine variety. So this story is reasonably well known. I mean, it's described in the case of compact groups in this book of Atiyah, the Geometry and Physics of Knots. So I was at Oxford at some point or other, and I was inspired by all of the talks there that people, basically all of the talks were some version of the geometry of some type of character space. And then you read the work of Dubrovin and others on Stokes data, and you start to understand that like vastly more is true, that basically all of the stories that people do here have an extension. There's far more spaces occur, and the way to get to it is to start at this full category of connections rather than just the category of tame ones, which has this topological description at the bottom. So here I could also just put, so here I'm looking at local systems of vector spaces. It's also, say smooth vector bundles with flat connection, with flat complex connection. So from a more differential geometric perspective, you could work in this perspective. But this is different to the algebraic perspective, and there's lots more here once you forget the regular, singular, or tame condition. So what we want to do is explain the line along the top, which has the parallel versions of this story. So I'll just draw the symbols which occur, and I'll spend the rest of the time explaining those symbols. And we want to end up to get to the same type of Poisson structure. We want to construct that by chopping up the surface into pieces. But that comes out when we write out explicit presentations of this fundamental group. So we'll have con will be equivalent to a category I'll call Stokes local systems. One of the difficulties in this subject is that there's lots of different ways to describe this category. I have a paper from March 2019, which describes 3 of the main ways of thinking of it and tries to give a fair and unbiased view of the history. But I want to focus on this perspective because this fits most nicely into this TQFT type picture that we want to get to, the quasi-Hamiltonian construction of these Poisson varieties. So this again has the property that we can get to these finite dimensional affine varieties. So we need to fix more than the rank. So we'll look at the Stokes local systems which have a fixed irregular class. So this is important because this plays the same role as the moduli of the curve. We had this base at the bottom over here before, which was the moduli of curve with marked points as well. In the full isomonogamy story, you also want to vary the irregular class. There's lots of interesting examples, even if you just take the sphere with one marked point, provided you pass this irregular picture. Okay, so I'll explain what that is today. That's the basic aim for today. But the story then goes as before, that you can look at the isomorphism classes of Stokes local systems, or if you prefer, the equivalent category of connections with fixed irregular class. And this will again be the set of orbits of a reductive group on a complex affine variety. So this will become the space of Stokes representations Hom S pi G modulo some group H. So we'll explain what this is probably tomorrow. And this will have some confusing notation to be the same as before, but this will be called the wild character variety. And this again has a natural algebraic Poisson structure, and leaves are got by fixing certain conjugacy classes. So we want to talk about this basically today, and what the boundary actually looks like when you have an algebraic connection, you go towards a puncture. Okay, so let me erase this and just write down. The point is that explicit presentations of such spaces have been known since the work of Birkhoff. So it's much easier to sort of understand what the presentations are than to understand what the intrinsic perspective is. And so probably here, people knew what representations of the fundamental group were before people had this intrinsic, sort of more sophisticated perspective. And so in the wild picture, this goes back to Birkhoff in his papers of like 1909 and 1913. So sort of explicit presentations. So this leads directly to this quasi-Hamiltonian picture that they appear as multiplicative symplectic quotients. So at the bottom, you would get this standard picture that you have some, you're looking at the space of representations of the fundamental group of a punctured curve. So suppose it has genus G, then you get the product of the multiplicative commutators, something like AI, BI, in a particular order from like 1 to the genus G. And then you might have these M punctures, so you get something like 1 to M of some matrices MI. And so these AI and BIs are all in our group G. And this is the multiplicative commutator. So the bracket of A and B is like AB, A inverse, B inverse. And this has to be equal to 1. So this space has an explicit description as a space of like 2G plus M matrices, which obey this one relation that this product has to be equal to 1 modulo the group G. So that's an explicit description of what we had there. Okay, so let me just adjust this slightly. So if you read Poincaré's paper, he does something slightly different. He chooses a base point near each of the punches. He doesn't just have the one base point, he has a base point near each of the punches. And so we want to define some base points B1 up to Bm and take pi, sort of this big pi, to be the fundamental groupoid of this curve sigma O with respect to this collection of M base points. So basically we're looking at homotopy classes of paths where the start and the end has to be amongst this collection of base points that we had there. So in effect, we're framing the local systems at each of these points rather than just at the one base point. So we now get an action of a group. So here, the group, which is H at the top, here in the tame picture, this is just G to the M, changing the framing at each of the base points. And then you can rewrite this rather than, so sometimes you also want to have this extra base point in the middle, and I think you probably want that here. So B prime is B with all of these base points as well, so B union beta. And then you would have pi prime with this beta prime here, so pi 1 sigma O. Yeah, so there's, in order to get the relation here, you need this extra base point in the interior as well. So then you just get the same as before, but the MIs here are replaced by C inverse HIC. So CI equals 1. So basically you have your base point near the puncture, and you have this connection matrix that goes from BI to this base point in the middle, B, and then you have HI is just a monodromy around a small loop at the puncture. And so in this tame picture, this is still HI in G. And then you go back along CI inverse. And now you have this action of this larger group, probably quotient by G to the M, to get the same picture that you had before. You're just simply putting in more base points there. So what Birkhoff did, he has this same picture, but for G to 0, but this picture here then becomes much more complicated. So basically, this part is replaced by something like C inverse H, and then a product of some Stokes matrices C. Stokes matrices, multipliers. So some products of Stokes multipliers like that. So we want to sort of understand intrinsically what these are. In the examples he looks at, basically S, or what he did was equivalent to just taking U plus cross U minus to some integer k. So these are the unipotent triangular subgroups of GLN. So U plus minus the unipotent radicals of a pair of opposite Borels, and so U plus is like 1 star 0, and U minus is the transpose of that. So this is really weird. I mean, the case he actually looks at had these factorized into a product of one-dimensional groups. And so geometrically, it's much less clear what's happening there. And so we want to gently, over the rest of the talk today and the talk tomorrow to try to understand intrinsically what these S's are. But the fact is, at the end of the day, you have an explicit presentation just as before, except in Birkhoff's picture now, H is in a maximal torus, so the torus acts by conjugation, and this group H, this H is the product of the tori. So if I have an irregular pole at each point, then you would get T to the M. And this is the generic picture, basically the picture that Birkhoff looks at. We want to understand what happens for an arbitrary connection, and then basically the groups here are block diagonal. They're graded automorphisms of a vector space, as opposed to full automorphisms in the picture there. So we need to understand this grading that happens at the boundary. And basically I want to spend the rest of the talk talking about the grading, and then we'll see how that fits into this Stokes picture. So so the basic picture will end up something like this, where the structure group gets broken at the, do you want me to look? The structure group gets broken at the boundary, so I might have something like GL2 here, but if I go right to the boundary and look at the formal classification of connections, then the structure group is broken to a maximal torus, typically. So it breaks from, say, GL2 to C star cross C star. So what's actually, what the boundary actually is might look like this. This is the picture which occurs for the linear equation which occurs for panel of A1. If you go back to Stokes' original paper, he looks at the Airy equation. He actually has a picture like this there, which is the projection of that picture. If you're looking at the solutions of Airy, then there's factors of like e to the z to the 3 over 2, and he's looking at the dominance between the two branches of this exponential factor which occurs. So the picture we want to get is a circle which double covers the circle of directions, and Stokes is drawing a projection of it here to indicate the dominance of these exponential factors which occur. So we'll try to make that precise in the next half an hour or so. And then the Stokes picture, so right near the boundary we'll get a graded local system, and the Stokes business is all about how to glue that, or the multi-summation interpretation of what Stokes was trying to do is about how to glue the graded local system at the boundary into the local system of solutions here in the interior of the curve. So basically we'll have the local system of solutions on a disk around each puncture. Then we'll have this other local system which is graded, which is to do with the formal solutions, and the Stokes business is about how to glue those together. There's a natural way to glue those away from each singular direction. And the singular directions were marked on Stokes' picture. These, the largest difference between the decay and growth of the solutions. Okay, so we need to sort of back up and be slightly more pedagogic and define what we mean by a graded local system, and that will give part of the extra topological data that we want to have here. So at the end of the day, we need the graded local system at the boundary that classifies connections formally, and then the Stokes business is about how to glue that into this local system V that we have before. Okay, are there any questions about this picture before I delete it? Is this vaguely clear? Is it? Okay. Okay, so let me just start off quite abstract. I want to define what is a graded local system. And then I'll explain how it occurs at the boundary of a connection, at the boundary of the curve when you have an algebraic connection. So I just want to start out with a circle I'll call partial, or curly D. And I want to have a covering space. So I is a covering. So this is a certain covering. Okay, so I mean, I didn't really define, so maybe I'll just mention like a local system of sets is the same thing as the sections of a covering. Sections of a covering. So the covering may have a, an uncountably infinite number of fibers, points in the fibers. And then a local system of vector spaces are the so you have constant clutching maps. So it can be described in terms of an open cover where the clutching maps are constant. So if you have a local system of vector spaces, it's the same. It's a special case of that, but you put in the condition that the clutching maps have to be constant linear isomorphisms of the vector spaces in the fibers. And you can have local systems of varieties, and you can have local systems of Poisson varieties or symplectic, where you put in the condition that the clutching maps have to be constant isomorphisms of algebraic varieties or constant isomorphisms of Poisson varieties. It's a useful language to use. So at the end of the day, the family of wild character spaces will be a local system of Poisson varieties over the space of admissible deformations of the curve plus the mark points plus the irregular classes. That's kind of what we want to get to. But here we're just looking at very simple linear local systems which occur out of connections. So suppose I have a cover, and I also have a, so V over here. This is a local system of vector spaces. So I have a local system of sets I and a local system of vector space, and I want to define what it means for V to be I graded. So V is I graded if, so I have a pointwise grading of each of the fibers. So V, so I choose a point D in the base, then I look at the fiber, so VD, this has to be graded by the corresponding fiber of I. And so this is like the sum for I in the fiber ID of subspaces of VD of I. So these are subspaces. So ID could be a lot larger than the dimension of V, so I'm happy for most of these spaces to be of dimension 0, and I just have a finite number of active or effective indices I. And then plus this has to be locally constant. So if I move D, these subspaces have to be related under the local system structure of V. And so in particular, if I go around the circle completely, I'd have a permutation of these subspaces, and that permutation has to be the same as the monodromy of this covering ID, the permutation there. So e.g., so if I have sigma goes from V to V, the monodromy around a positive, around the circle in a positive sense, I have sigma hat, the monodromy, so this is from the fiber here, so ID from some base point D to ID there, then sigma of VD of I has to be equal to VD of sigma hat of I for all of I in ID. So that's a consequence of the fact that this grading is locally constant. So we have a precise definition of what we mean by a graded local system. And these things actually occur when you look at the formal classification of connections. But the monodromy of this may well be different to the monodromy of the local system that we had before. And so we'll call this V0, the graded local system. Okay, so that's the abstract picture. Now we want to take so I have a point. So A is a point of some it's a point of our curve, and we've chosen a small disk around it. So this leads to, so partial is the circle of directions, the real oriented directions at this point. So if you like, I would look at the tangent space of A of this disk, and I'll puncture it like this, and I'll quotient by R plus. So it's the real oriented direction. So I have this disk with the marked point, and I get this sort of delta hat. The real oriented blow up like this. I'm replacing the point by this circle of directions. And the basic fact is that there's a natural covering space of this. I'll call this the exponential local system. So it's a local system of sets. It's a huge covering space of this circle here. So each component of it is a circle. There's no component which is an infinite cover of the circle at the bottom. So maybe I'll define that in the moment. It has the property, the main theorem. So this is Deligne's way of stating the formal classification, and the formal classification is due to lots of people like Fabry, Hakahara, Taratin, I'll just abbreviate people's names, Fabry, Hakahara, Taratin, and Levelt. So this is Deligne's nice way of stating it. So we want to look at formal or connections on the formal punctured disk. So E nabla, so the category of connections on the formal punctured disk. So if I choose a coordinate and a local trivialization, basically I'm looking at the group with values in the formal Laurent series. The category of connections on the formal punctured disk is equivalent to the category of I-graded local systems. So I have this huge covering I, so I can look at the local systems of complex vector spaces which are graded by this. So I-graded local systems of complex vector spaces. So we're encapsulating lots of statements there that people have looked at how to simplify connections by using gauge transformations in this group, and generically it's possible to diagonalize the irregular part of the polar part, and then it's graded by this polar part. And so what this I is the space of irregular parts of the eigenvalues at the pole of the connections. So we want to make that precise to define what is I, but at the end of the day it's something like part of the eigenvalues at the pole, and it's kind of a surprise that these can be defined because we're working at connections with gauge transformations and not just by conjugation, but nonetheless these do have sort of irregular parts of eigenvalues. And so we'll define what is I. So basically, for experts on differential equations, it's just the exponential factors which occur. So it's a huge union of circles. These are circles, and they're generated by the exponents which occur. So you might have a solution of a differential equation which has an e to the q, and we're recording the q here, which occurs. So the problem is that these q's may have roots of the local coordinate z. So local sections of I are functions on sectors at the pole that can be written of the form So something like Q is sum AI Z to the minus I over R. So AI is a complex number. So R greater than or equal to 1 is an integer, the ramification. And Z is a local coordinate vanishing at the pole. So it's like I from 1 to some integer k. So all of the functions that can be written like that for certain choices of branch of log z. So there's an intrinsic definition. If you look at the paper with Daisuke from 2015, there's a way to define this intrinsically without choosing a coordinate, and then you have to talk about certain equivalence classes of functions. But effectively, you can just work with the functions, and then it's e to the q, which occurs in the solutions of differential equations. So if I have a section like that, I get a circle, which is something like the Galois orbit of Q. So generically, I would go around R times for it to come back to itself. And so I'll like the ramification of the circle Q is the R, which is minimal, which can occur. And so for example, you could just take Q to be a polynomial in 1 over Z. So Q in like Z inverse, C Z inverse. This is the unramified case. But also you have all of these cases which have ramification. And the case looked at by Stokes for the area equation, which gave this picture here, was Z to the minus 3 over 2. So even the simplest examples do have these ramifications. Okay, so that's slightly hard to swallow all in one go. Let's go back to talking about eigenvalues of matrices depending on Z, and then this might be slightly more clear.
Just a question.
Yes?
That this joint sum is over what once we write the Q like that?
Well, I take all of the functions that can be written in this way, and then each of those functions generates a circle. And then you need to say when those circles are the same. So I'm defining all of the circles, and I'm taking the disjoint union over the circles. So it's kind of a circular definition. It's the union over the pi0 of I, the number of connected components. But it's all of the functions which occur. There's a special circle, the tame circle, which is just 0. So all of the story at the bottom of the picture that we had before is grading everything by this tame circle. So there's all this other stuff which occurs, and these have deformations just like the moduli of the curve. So I'll give some examples of how these occur. Yeah, maybe. So maybe first of all, I'll just mention the class. So if V0 here is I graded, the class is so if this local system is graded by this cover here, there's only a finite number of circles which actually grade a part of it of positive dimension. So I get some finite sum. So this is like 1 to some integer. I don't know. I had k before, but this may be a different k to the k which I had over there. So these are the circles. So the effective circles. Effective, or if you like, the active circles. So there's a finite number which grade a positive dimensional bit, and the ni's is the dimension of the corresponding graded piece. So the rank of V, so we had this n, which was the rank of V, which will also be the rank of this 0, this should be, so if I sum over each of the fibers, I get these ni's repeated ram qi times this, like ni ram qi. So for instance, in Stokes's example, he had n equals 2. He was looking at the area equation of second order, and he had multiplicity 1 and ramification 2. So it's have these two vector spaces of dimension 2 broken into these two one-dimensional pieces, and these get swapped over if you twist around the ones. Okay, so there's various examples. The first is perhaps to look at rank 1. So here you're just looking at a differential equation which is like d minus a of z dz for some meromorphic function a of z. Well, let's say h of z. So I want a meromorphic 1 form there, and I'll write it as dq plus lambda dz over z plus d of something holomorphic. So this part is holomorphic. Lambda dz over z is the residue. I just have a complex number here. And here I get my q, which is in z inverse c of z inverse. So that's the basic example. And then these solutions of this are proportional to things like e to the q z to the lambda multiplied by something holomorphic. So we see that the wild part of the solutions, the part which has like e to the 1 over z or a polynomial in 1 over z, comes completely from this irregular part here, Okay, so then you can look at a matrix equation, and generically you'll be able to diagonalize this irregular part, and you'll get something like q to be diag q1 to qn, where each of these qi's is also a polynomial in 1 over d minus dq plus lambda dz over z plus something holomorphic. So this is the unramified case. So the class of this will just be the z inverse c z inverse. The class of this is just the qi's plus their multiplicities. So some of these might be repeated. And if I did this where q is equal to 0, I do get back to the tame picture. It really is a special case of what we do, where we would just have a logarithmic connection having this first order pole. So to go beyond that, we need to sort of try to work out what the Eigen values are in general. In general, so the statement is that we can pull back. There exists an integer r, so you get something like z is equal to t to the r. So we pull back from the z disk to the t disk. We can pull back such that we can get to this picture here, and then these q's will be polynomials in 1 over t, and that is the class that we have over there. So this is just an intrinsic way to talk about how to pull back and straighten out if you actually can't straighten out at the bottom. And this is not surprising. If you look at CF a meromorphic Higgs field, so Higgs bundles are simplifications of connections where you have the Leibniz rule simplified by forgetting the differentiation parts. So we'd have like phi of fs is f phi of s. So a Higgs field is a simplification of the connection. It's just basically in a local trivialization, it's a matrix of 1 forms. It's not differentiating. Once we have this, I mean, you can then just look at the eigenvalues. So look at the characteristic polynomial. and the roots of this are the Eigen values, and you get these Poisson series. And you have a Jordan form that you can pull back and it all straightens out, that your eigenvalues will then be unramified. So here it's clear that this statement holds, that you can pull back to straighten out the irregular part. The off-diagonal part in the Jordan form can be taken to be constant, so it does not affect the irregular part. The theorem of these people says that that works for connections also. You can't define all of the eigenvalues, but you can define the irregular parts. And so, in particular, each connection gives me a graded local system, and it gives me an irregular class. So this is the irregular class. So I'll sometimes write this as theta. So it can also be viewed as a map. So from the set of circles, the pi 0 of I to the integers n, so just taking a circle to the multiplicity. So there's only a finite number of circles where you don't get 0, and that will be this ni, which is here, ni. There's various different ways, but the fact is any connection has a canonically defined irregular class, and it occurs in the gradings which classify the formal connections here. So a connection gives you a graded local system. I mean,
is I always a compact cover of the circle, or is it?
Each component is compact, but it has an infinite number of them.
Always this script I has infinite. Okay.
Yeah, it has one for each of the functions, and even if I just look at the ones which are untwisting, this is a subset of the pi 0. Each point of this is a component of, each point of this determines a component of I. So there's lots of them. Okay, so really what Deline does here is take the monodromy of the graded local system. Okay, so these people say that you can pull back to get a graded connection, that you can kill all of the off-diagonal parts, that you get to something like this, and then the Q will enable you to, maybe I'll spell this out better. Okay. Yeah, so it's more that Deline is talking about sort of a formal version of Riemann-Hilbert, that the statement is that you can pull back and get a connection. So basically your connection can be put in the form something like d minus dq plus lambda dz over z plus something holomorphic. And so you would define, let me look at the untwisted case. You would take H to be the centralizer in the Lie algebra G of Q. So Q is basically a list of diagonal matrices. So AI over Z to the I for like 1 to K. Right. This is a diagonal matrix with elements in here. So it's basically this list of diagonal matrices. AI is a diagonal matrix T. And I just want to look at the subgroup of, sorry, this is the centralizer in G. So the n by n matrices which commute with each of these AIs. So if the AIs are sufficiently generic, H is a torus, whereas if Q is equal to 0, H will be equal to G. And in general, you get these block diagonal subgroups. It's basically the same as the graded automorphisms of a fiber that we have over there. So formally, you can put it in the form dq plus lambda of z dz, where this takes values in the Lie algebra of H. So you can actually kill all of the off-block diagonal pieces if you work formally. So this is what I mean by a graded connection. It's graded by these principal parts. And then we're taking the monodromy of that to get the graded local system. Monogamy of this equals the graded local system and I'll be calling this V0 at the marked point 0. So that's like the coordinate dependent way to do it, that you want to be able to straighten out your connection in this way and then take the monogamy of it. And this works in general by passing to covers. There's an intrinsic way to define what the graded local system is. Basically, you can define the Stokes filtrations and take the associated graded of that, and that's completely intrinsic, and that will be isomorphic to whatever graded local system here if you work with these series in a coordinate Z. I'll just mention that. I don't know if I'll get to that tomorrow, but the basic picture is that formally you get this graded local system at the boundary. So I'll draw the picture which will sort of preempt what we want to get to tomorrow. So I have this disk in our curve, and I have a marked point having a puncture. And I then do this real blow up, and I get this circle of directions here. So it's as if I've chopped out a disk, and so here I'll have like a G boundary there. So in a germ of a punctured disk, in a small punctured disk around the pole, I'll have the local system. So I'll draw this here, and that becomes some annulus here. This I'll call the halo, like a annulus. And on the halo, we now have two local systems. We get V restricted to H, and then we have this graded local system as well. So H is homotopy equivalent to partial, so I'll not really just distinguish between the circle and H. But the fact is we have this graded local system also, and the Stokes business data is equivalent to gluing V2, V0 away from the singular directions. And then the magical fact is that this can be axiomatized. And if you look at all of the things which obey the axioms, you do get a purely topological description of the category of connections. I first learnt these axioms from papers of Martinet-Ramis and Lode-Richaud, but there are equivalent axiomatization in the papers of Balser-Jerkat and Lutz, and there's this Stokes filtration perspective also, so there are at least three different perspectives. And the generic case goes back to Birkhoff. So next time I'll talk about what the axioms are and what the definition of these singular directions are. These are the Stokes lines which were in the last talk, but there is this debate about whether to call them Stokes lines or anti-Stokes lines, and so perhaps we'll stick with singular directions here, and these will be called a set A. No. Okay, I think I've got 3 minutes to go. I mean, the bit I skipped over, which I didn't mention at all, is the third algebraic structure. We had this picture. Maybe I'll just mention that to end, but it's kind of taking us slightly too far afield. There's this notion of sort of non-abelian Hodge space. This is sort of described in this survey paper on the archive for Hitchens' 70th birthday. So you want to try to axiomatize the objects which occur, and we were having this sort of moduli space of connections, and there's some moduli space of Stokes and monogamy data here, and there's this sort of Riemann-Hilbert-Birkhoff isomorphism, which, when interpreted properly, is a complex analytic isomorphism between these two algebraic spaces. But there's this third picture, the Dolbeau. So for me, this will be meromorphic Higgs. Lots of people have worked on the holomorphic or non-singular picture, but it extends to this picture. These are the meromorphic Hitchin systems. So basically, Hitchin looked at the case with no poles, and there's earlier work in the integrable systems literature, I think first going back to Garnier in 1919. He looks at the genus zero Hitchin system, if you will, which is sometimes called the classical Gordon model. Basically, he started in the Dirham picture. He looks at the Schlesinger equations there, which are the isomonogamy equations, and he looks at the autonomous version of those, and he got an integrable system which he integrated with a billion functions. And these, the Garnier picture and the Hitchin picture, were kind of put together in the mid-90s in this work of like Markman and Botochin, purely from the perspective of algebraic integrable systems or Poisson algebraic integrable systems. But these fit together that you do have this like wild non-abelian Hodge. And this is a complicated thing that passes through these spaces of solutions. So this is sort of solutions of Hitchin's equations on the open curve. Solutions of Hitchin's equations, or if you like, harmonic bundles, Hitchin's equations on sigma O. So you have to understand all of the boundary conditions. So basically one can define a functor from here to algebraic connections. This was looked at in the compact case, I guess, by Donaldson and Corlett. Separately, Corlett did this in arbitrary dimension. It was extended to the wild picture by Sabat in 1999, and proving an equivalence here. Sabat restricted to parabolic weights, the Betty weights being trivial, but it's possible to extend what he did. And then one can extend this to over here in the usual picture. This is introduced, I guess, Hitchin and Simpson. And Simpson is extended in the wild case in this paper with Bickard. So Bickard, in like, I think it's published in 2004. So there's an equivalence there. So these are just different algebraic structures on this hypercalar. This is a hypercalar manifold. The approach of Hitchin that was extended in this work gives this the structure of a hypercalar manifold. And we prove that it's often complete. So you get this large class of complete hypercalar metrics. The ones that occur for Panlevet equations, that's where the fiber is complex to dimension 2. These are what the physicists call gravitational instantons. So we get a sort of a class of gravitational instantons basically coming out of the work of Panlevet and the more recent extensions. So this definition is aimed because you want to try to classify these structures, this hypercalar space with this triple of algebraic structures. When you actually write down the Panlevet equations, you want to approximate this. So if you look at the case on P1, there's this open part, sort of M star, and this plays the role of the Lie algebra. So I'll probably talk about this in the third talk, that there's very simple to construct algebraic symplectic structures here. And so basically the Riemann-Hilbert-Birkhoff map can be most easily tasted. So I have an algebraic inclusion there. The transcendentalness of the Riemann-Hilbert-Birkhoff map is like best like tasted or seen by looking at this map, basically connections on the trivial vector bundle on P1 with arbitrary order poles. So this has a very simple symplectic structure, and the multiplicative symplectic structure we'll get to here is a multiplicative version of the usual symplectic structure we'll get there that should appear in 2 days' time, the third talk. I'll stop there.